Hi there, I'm Lauren, and what I'm going to be doing are presenting these videos for you guys. I'm just going to give you a lecture on each section that we cover in the book. I encourage you certainly to read the book prior to watching these videos, and then I think that the next best step would be to watch the videos, and then you should be ready to go and do your homework, etc. I try to do examples that are similar to many of your homework problems, and so I hope you find these to be very helpful. All right, so I'm going to begin the course with Chapter 6. I know it seems kind of strange to run the course out of order. However, I think that the course flows better when we do the probability and statistics first, and then we get to the linear math at the end of the semester. One comment that I'm going to make is I will be giving you various definitions. I don't ask you to give me definitions on any test or quiz. The reason for these definitions is just so that we're all speaking the same language and there's no misinterpretation as to what I mean. All right then, so I would like to get started with section 6.1. And this whole chapter is on sets and counting. So what I'm going to do with section 6.1 is give you a very general definition of what a set is. A set is a collection of objects that may or may not have some property in common. All right, now I know this is a very general definition, but it is meant to be such. So we could talk about the sets of lots of things. I mean, we could talk about the set of students in Math 115. We could talk about the set of all regular polygons. We could talk about sets of really virtually anything. These two sets happen to have something in common, but again, they don't need to. So, an example of a set that I'm going to give you right now that I'm actually going to write out is, how about the set of digits? This is something that we use very often in this class because it works well for various examples. Okay, so a couple things to point out. One thing that I want to point out is that we name sets. Nothing unique, but we name them with capital letters. Okay? And the way we write sets is, well, I'm going to call my set of digits D. Again, no originality in there. And when you write out a set, you have these funky little curly braces. Okay? So what I'm going to do is I'm going to list all of the elements in this set. So the set of digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Not very thrilling. Now, there's other ways we can represent this set. Another way I can write this set is I could say 0, 1, 2, all right, you got the point, and it goes until 9. Okay? That's kind of my style because it's a little lazy approach. A third way we can write a set, and you're going to see this in your book, is using something called set builder notation. Okay, so let me write the set of digits using set builder notation. UIL. Okay. And the way we would write out this set, it's the set of all x such that x is a digit. And underneath, I'm going to write how we read this. So that says the set of all x, okay, set of all x, this vertical line says such that x is a digit. Now, on one hand, this is a fine way for writing sets. On the other hand, if someone didn't know what the set of digits are and what the digits are, this really wouldn't give you any information at all, okay? So when you can list the members of the sets, sometimes it's helpful, okay? So while I'm on this note, and I caught myself saying it, when we talk about the members of a set, there's actually a name for that. Okay, so the members of a set are called elements. Alrighty, so for example, with our set of digits, I think you'll grant me that 5 is an element of D, because 5 is a member of my set of digits. Now, it would be a real pain to always have to write this out. So what we have is we have notation for this. Okay? Notation in mathematics is not meant to confuse people. It's actually just sort of a lazy person's approach for writing things. So the way that you would write that something is an element of D is I would write 5 is an element of, that's what this says, D. Okay, it looks like a little epsilon. Okay, now I think you'll all grant me that 11 is not an element of D. So, just like how we say that two things aren't equal, we have an equal sign with a slash through it, that's exactly what we'll do here. So the way to show that something is not an element of is we would write 11, and then we would write this element of, but with a slash through it. And there we have it. Okay? So please don't get caught up in the notation. It's really just meant to simplify things. All right. So the next thing I want to mention are just a few little particulars dealing with these sets. One thing that I would like to say is that we can talk about something called the empty set. As you would probably imagine, the empty set is the set with nothing inside of it. And we have two ways that we can write the empty set. You could write these little curly braces with nothing inside, or you could write what we call the empty set symbol. Okay? Either one of those are absolutely fine ways to write the empty set. One little catch, don't do this. This is not the empty set. It's actually a set with one element, and the element is precisely the empty set symbol. So, big red X here. Don't do that. Okay? Now, something that might seem fairly clear to you is that two sets are considered to be equal if they contain the same elements. I think that's probably a pretty obvious statement, but what I would like to say is, for example, this set, 1, 2, 3, I claim it's equal to the set 2, 3, 1. And the only point that I'm trying to make is that the order in which you list the elements doesn't matter. Okay? All right, one more little guy in here. What I'm going to do is define a couple of sets right now. So, I'm just going to randomly come up with a few sets, or two sets, how about? Suppose my set A consists of 1, 2, 3, and 4. And suppose I have a set B, and let's just say B is 1, 2, and 3. Okay? Would you grant me that every element in B is also in A? Yeah, right? 1, 2, 3, they're all in A. When that's the case, we say that B is a subset of A. Now, just like we had notation for things being elements, we also have notation for subsets. The way we would write B as a subset of A is you write B is a subset of A. Okay? I think you will grant me also that this is a true statement, that A is a subset of itself. I mean, it's kind of a redundant statement. Every element in A certainly is also in A. Okay? So, my next question relating to subsets is the following. Is A a subset of B? What I'm asking is every element in A also in B? Okay? And I claim the answer is no. And the reason why is because, watch this notation, 4 is an element of A, but 4 is not an element of B. Okay? All right, so continuing on in this section, what we're going to do is talk about various set operations. So just like with numbers, we have various operations that we do. With sets, we also have various operations. There's 3 operations that we're going to discuss. So, let's do them. Now, as I'm describing these set operations, what I would like to say is that I'm going to be drawing pictures. They're called Venn diagrams. If they're new to you, you're about to see them. Venn diagrams are really, really useful ways of depicting sets, and hopefully you'll see their usefulness. So, before I talk about various set operations, I need to define one more thing, okay? What I need to define is something called, that I'll call with a script U, it's called your universal set. And the universal set is essentially the set of all elements of interest in a particular situation. When it's relevant, your universal set will always be given to you. Okay? And the reason why I say it's the set of all elements of interest in a particular situation, depending upon what we're talking about, our universe is going to change. All right? So, you don't have to come up with what the universe is. That's just something that will be given to you. All righty. So, the first set operation I would like to talk about is the following. Okay? Let's suppose also we are given sets A and B and U, our universal set. Okay? So the first set operation I would like to mention is written like this. A, and it looks like I have an exponent of a C. What that means is it's the complement of A. And what the complement of A, or similarly A complement, consists of is it's all elements in the universe that are not in A. So, I think that very often pictures are worth a whole lot in mathematics. So let me draw a picture for you of what A complement looks like. So, in general, we depict our universe to be this box. So this is now my universe. And suppose this is A. Okay, so you might ask, well, what is A complement? Well, it's everything in my universe except for what's in A. So the way I would shade this Venn diagram is I would cover up A and I would shade everything around it. All right? So that's our first set operation. The next set operation that I'm going to talk about is called your intersection. Okay? And the notation for that, an upside down U, that's called A intersect B. And I'm going to write this out in set builder notation just so you get used to it. Okay? It's the set of all x such that x is in A and x is in B. So what we're looking at with the intersection is what these two sets have in common. So let me draw you two alternative universes and we'll see how they look. Here's one universe, and suppose this is my set A and that's my set B. If I want to know what these two sets have in common, I'm looking for the elements that are in A and in B, and I claim it's just right where they overlap. Now, another way this can appear is the following. Suppose A is here and B is out here. Do these two sets overlap anywhere? No. Okay? So, what we do when there's no overlap, we say that A intersect B is equal to the empty set. And these two sets then are called disjoint sets. That's when they have nothing in common. All right, one more set operation here, and then we will practice working some examples, okay? The third set operation that I would like to show you is called the union. And the symbol for that is a U, okay? When you're unioning two sets, you are literally just putting them both together, okay? So you don't really have to pay attention to what's in common. You just take set A, take set B, put them together, and there you have it. So we say it's the set of all elements X such that X is in A or X is in B or both. In other words, it can also be in my intersection. So let me draw a picture here. One possibility, again, is here's A and B, and I claim that my union looks like this. Because these guys are in A, therefore they're in the union. These guys are in both, therefore they're in the union. And these guys are in B, again, therefore they're in the union. Okay, my alternative universe could look like this, where A and B have nothing in common. And then what we can do is say, all right, well, here's A, here's B, and now I've shaded my union. All right, so that gives us our general 3 set operations. And what I now want to do is play with some examples, okay? So then, let's start with this. Okay, one possibility is I could give you, say, my universe. And let's pretend our universe is 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay? And I'm going to define my set A to be 1, 3, 5, and 7. I'll define my set B to be 2, 4, 6. And I'm going to define my set C to be, how about 6, 7, 8, and 9. Okay? I'm just going to play with a few set operations here so that you get the hang of it. This is one scenario where you're going to see these things arise. Now, just like we have order of operations with addition, subtraction, multiplication, and division, and parentheses, and all that fun stuff, we also have order of operations here. The key thing is, if there's parentheses, you always do what's in your parentheses first. So, the first thing I'm going to do is, let's first find, oh, who cares? How about a complement? Okay? A complement is everything in my universe except for what's in A. So I claim a complement is everything except 1, 3, 5, and 7. So it's 2, 4, 6, 8, and 9. All right. Well, what if I asked, what is a complement? How about intersect C? What I'm asking here is the following. I'm saying, hey, take your set A complement and ask what it has in common with your set C. Now, one comment that I need to make is, yes, we already found A complement, but if we hadn't, you would need to do that prior. All right, so now that we have A complement and we have C, we ask what do they have in common, and I claim they have 6, 8, and 9 in common. All right, what if I wanted you to take, how about B union C? Now I'm doing a union. All I want to do is put them together. So, let's see. We have 2, 4, 6, 7, 8, and 9. All righty. Let me just do a couple more examples with this. Suppose I want to take A and I'm going to intersect that with B union C complement. All right, now it's getting big, okay? So, watch your order of operations. You look at this, the very first thing that you need to do is say, I need to find B union C. You need to have that. Now, I claim we've already done it, so that's cool, okay? Now, my next step is I need to then take the complement of that set. All right, well, since B union C is over there, let's find what the complement is. Remember, the complement is everything in our universe except for what's listed there. So what do we have? 1, 3, 5. And I think that's it. All right. Now that we have that, I'm going to intersect that with A. In other words, what does A have in common with this set B union C complement? And I claim that they have 1, 3, and 5 in common. So you see, we build these things, and the order is really, really super duper important. All right, So this is one way that we're going to be playing around with these set operations. Another way that we could be playing with these set operations is the following. So suppose now I tell you that our universe consists of all students at UM. Okay, nice little verbal description. And let's have the set T, and let's define it to be, okay, T is in my universe. Let's have it be everybody in the universe such that those people drink tea. So these are our tea drinking students at UM. And why don't we have C be the set of all people at UM, students specifically, such that they drink coffee? Okay? So, something that I could ask you to do is to give a verbal description of, and let's just do, how about 2 examples, okay? One we could do is T intersect C. Remember, we want to know what they have in common. Now, the first thing you have to do when you give a verbal description is you have to acknowledge your universe. In other words, I would recommend always start with a blurb about it. So, all students at UM who, well, drink tea. Your intersection says and the C says drink coffee. Okay? So this brings up something quite important. When you have the intersection, your key word is and. And when you have the union, your key word is or. So, let's just do one more verbal description. What if I want T complement union C? I claim this is the set of all UM students. I'm acknowledging my universe. Who, well, T complement, well, who do not drink tea. The union says or drink coffee. And then we can acknowledge or both. And that's how our verbal descriptions work. All right. Last but not least, we can shade Venn diagrams. Some people love shading Venn diagrams, and some people do not love shading Venn diagrams. So I guess what I'll say here is it's important to know what various parts of a Venn diagram look like, but this isn't a huge thing to stress out about. Well, hopefully none of this is. Okay, so let's shade the following. What if I want to shade A complement intersect B? Now, when doing Venn diagrams, I always recommend either use different colors or do them in various stages, okay? I simply cannot emphasize that enough. So, here what I'm asking is what does A complement and B have in common, okay? So, let me first acknowledge A complement in blue. Remember, A complement is everything in the universe except for what's in A. So, will you grant me that's what's either in this region or this region out here? All right, that's A complement. Now, I'll do B in red. I think you'll grant me that B is this region and that region. Okay? So, since I'm doing the intersection, I want to know where do I have a red X and a blue X. And I think that you will grant me that this is the only region where such is the case. Therefore, this is my final answer. Okay? So, let's do this guy. What if I want to do, I don't know, how about we shade A complement union B complement? I don't think the union is quite as satisfying as the intersection, but it's easier actually, because when you're doing the union and you're shading, all you do is you shade this first guy, you shade this next guy, and walk away, because then you're done. You've shaded everything that's in this or that or both. So, again, A complement, cover up A. I think you'll grant me it's what's here and on the outside. All right then. Now, what's B complement? Here, let me show you. I did A complement in blue. We'll do B complement in red. I cover up B, and I shade here, and again, I shade what's out here. I claim I'm done, okay? Our answer is everything but this inner wedge, okay? All right, so we could also do a Venn diagram with 3 circles if we wanted to. So let's just do a couple examples there. What if I want to look at, say, A intersect B union C? All right, first let me draw a picture. Of these guys. All right, before I actually do any shading, I just want to make a couple comments about this Venn diagram. Okay? First off, this whole thing is my universe. A lot of times students just think the area out here is one's universe. It's the whole thing, okay? Now, this region I claim is only in C. This is only in A, and that's only in B. I claim this wedge right here is in A intersect B. That's A and B, okay? This part also includes C, but this does not. Just like this wedge is B intersects C, and this is A intersects C. All right, this guy here I claim is in all 3 sets. It's in A and B and C. All right then, so what I'm going to do is I'm going to say, oh, I got parentheses. I got to shade what's in my parentheses first. So why don't we do that in blue? And what I want to shade is B union C. Now when I'm shading B union C, I don't care about A at all. So I'm not even paying attention to A. There is B union C. All right then, next we want to shade A. I'll do A in red. I claim A is right here, and right there. Now, if I was doing the union right here, we'd be done, but I'm doing the intersection. So what I'm asking is, where did I shade both red and blue? And I claim that my final answer is this. Claim the places where I shaded both red and blue, one second, are right there. Okay? All right, so I'll do one more of these, but my biggest piece of advice is especially when you have 3 circles, don't try to do it all at once because you're just going to get bogged down. okay? Do it step by step, and I assure you it will be a lot simpler. So, how about this guy? Let's do, I'm just making this one up, so let's see how it comes out. How about A union B complement intersect C? Okay? So, where do I start? Again, I'm going to start in parentheses here. The first thing I'm going to focus on here in this first picture is figuring out what regions are in B complement intersect C. Okay? So, I'll do B, it would be nice to label our circles. Here's A, B, C. So, I will do B complement in blue. B complement is everything outside of B. So I cover up B. I'm going to put X's, I think, just to make it a little simpler. And I claim B complement is represented with these X's. C is all of that. All right. Now, if I want the intersection, I'm asking where do I have both a red X and a blue X, and I claim it's in these two regions. So, that was my first drawing. Now let's move on to our next one. Alrighty, so I claim at this point, here let me write this down, A union B complement intersects C. I claim at this point I have my regions of interest to be this and this guy. Okay? Now, notice I'm unioning that with A. I'm not asking what they have in common. If I was doing the intersection, I claimed this little wedge right here would be our only solution. But since I'm unioning it, all I'm going to do is take this, and then I'm going to say, well, I'll just color in A. Here's A, I've already colored him, this part, and that part. So I claim anything that's in blue or green is our solution. All right, that completes section 6.1. Have fun.